In this lesson, we'll talk about continuity and one-sided limits. We've already hinted at the notion of continuity in that I said certain functions have where the limit and the function value are the same. This is actually precisely what continuity is. A function is continuous at a point when we have these three characteristics. You need a function value. If you don't have a function value, the function's not continuous. You need the limit existing, and they need to be the same. Really, continuity and the idea of substitution are the same thing. Anytime you can just use substitution and plug in the value directly, that gives you what we call continuity. And vice versa. If a function is continuous, you can just use substitution to take the limit. Anyway, continuity can be on more than just a single point. It can be on an open interval, in which we just say the function is continuous everywhere on that interval. And it is also possible to be continuous on the whole real number line, and a lot of functions we've dealt with are like that. We'll talk about that in a moment. But anywhere, we call that everywhere continuous, or just sometimes we'll just say the function is quote-unquote continuous. Little note here that the domain of the functions, we'll talk about this soon, like the square root function is a little different, but in general, many functions are continuous on their whole domain. We'll talk about that. We have three different types of discontinuities. So first off, a discontinuity is a point where the function is defined around this point, but it is not continuous at that point. So there's actually three types of discontinuities, but we'll talk about the three as two for the moment. First off, a removable discontinuity is a hole in the graph. Anytime that we've had a hole in the past, we actually call that removable, and we'll talk about why, because in those cases, really it's just a single point. If we were to define the function to fit it, it would work just fine. Next is the concept of a non-removable discontinuity, in which we cannot just fill in a single point and fix it. F of x equals 1 over x. If we draw a picture of this, 1 over x looks something like this on both sides. It's got a branch above to the right and a branch below to the left. There's definitely a discontinuity at 0, but nowhere else. So at 0, there's a non-removable discontinuity, and specifically we would actually call this thing a infinite discontinuity. This is where we split apart the non-removable a bit. Non-removable in that there is no way that I could put a new point into this graph to fix this. The limit just flat out doesn't exist in general. Next one. Now this one is undefined at 2. You can see that by just looking in the denominator. At x equals 2, I would get a 0. But I can go a little bit further if I notice this factoring trick we talked about in the next lesson can be done here. As it turns out, I just get x plus 2, but there's a little note here that x does not actually equal 2, because that would have made this cancellation make no sense. You can't have a 0 in the denominator regardless. What that boils down to is the function looks like the graph x plus 2, which is a line, but at x equals 2, we have a hole in the graph. Otherwise, the graph is fine. With that said, this is what we call a removable discontinuity. And this doesn't get classified any further, we just call it removable. A hole in the graph is a removable discontinuity. The reason we call it removable is if we were to define the function to have the value of 4 at the point x equals 2, which is the limit, then the limit and the function value would be the same. Next example. This one will draw a picture. And I know for some of you the idea of a piecewise function is a little bit foreign, but I'll help you through it. What we do is we look at this characterization here. This says if x is less than or equal to 0. So I'm going to draw the graph of x minus 1, but only where x is less than or equal to 0. So let's see, the y-intercept would be negative 1. And the slope would be positive 1, but I only am going to draw this for values smaller than 0. So with the slope of 1, it's going to look something like this. And I don't draw to the right because it's a piecewise function. It's not defined at this part when x is positive. However, when x is positive, the function says use x squared minus 1. we could plug in a few values, but x squared minus 1 is a parabola that's been shifted down 1 and actually matches right here at the same point. At this negative 1 would be where the vertex of the parabola would be, and so I'll just pick up where I left off. With that said, this function is continuous everywhere. You can look at the picture and see that there's no discontinuities. Next example, also a piecewise function, but we can handle it. This time it's just x if x is less than or equal to 0. So that's the line y equals x, which is a straight diagonal line. And the next one is 1 minus x if x is greater than 0. 1 minus x has a y-intercept of 1 and a slope of negative 1. The y-intercept is 1, but here's where these get a little strange. When y equals 1 and x equals 0, the function is not defined. So what we have is actually a hole here, because it is defined to the right of it, but at that single point there's a hole. And if this is a little bit strange, just pay more attention to the pictures, because that's what I'm focusing on here. As you'll notice, this does have a discontinuity at 0. You cannot just pick a function value that'll fix this issue, so this is a non-removable discontinuity. And this has a different classification. You'll notice that this one is not infinite this time. It's non-removable, but it's not infinite. We call this a jump discontinuity, because the function jumps from one point to another somewhere along the graph. We've actually seen an example of this somewhere when we were taking limits. This is the idea where the left and right hand limits are not the same, which we'll define more formally here in a moment. Here is the idea of a one-sided limit. A one-sided limit, we've talked about how when you take a limit, you have to come from both sides. Now, we don't want to come from both sides for these. We just want to be able to come from one side and take a look at, well, what is the trend in the graph just from the left or just from the right? That's what this notation means. So when we see the x approaches c with a minus, that is a limit from the left side. The limit from values negative of that value, if you will. C from the left means we just look at the trend in the graph as we're approaching from the left. Whereas if we write the limit as x approaches c with a plus, that is the limit as x approaches c from the right. From a minus, that means from the left. From a plus, that means from the right. Now, there is some stuff here about the epsilon delta definition to this. If you're a math or computer science major, you might want to process that a little bit and think about it in terms of the one I said before, because again, this may show up in future classes. If you're doing a biology major, then we're really more interested in, can you take limits from the left and from the right? For the next example, we want to find the value as the limit as x approaches 3 from the left. Make sure that you can state the difference. Minus means left, plus means right. Of the graph of the square root of 9 minus x squared. Now we could draw this by plotting points, and feel free to do so. You'll notice that the smallest value that you can put in this graph is x equals negative 3. And the largest one that you can put in is x equals positive 3. But let's just plug in a couple. At negative 3, I was to get 0. At positive 3, I get 0. At 0, I get 3, and I get some values in between that I have to approximate otherwise. Whatever the case, when you draw this, this turns out to be a semicircle. And so now reading the value of the limit is just looking at it from the graph's sake. As x approaches 3 strictly from the left, you'll notice the y value approaches 0. And that's the answer. Now you'll notice there is no approaching from the right, so it wouldn't even make sense to talk about the limit as x approaches 3 in general. Just 3 from the left. Here's a nice theorem, and I've mentioned this idea a little bit before. The limit exists and equals a value if and only if the left and right hand limits are the same value. In other words, if the left and right hand limits are the same, then the limit is that value. If they're not the same, then the limit does not exist. Another thing that could happen is if one of these limits, the left or the right, did not exist, then the whole limit would not exist. This gives you a new technique. If the left and right hand limits are different, the limit does not exist. Now we can make one more definition of continuity. We can talk about continuity on a closed interval, and this is the way we do it. You need continuity on the open interval. you need a limit from the right to work on the left endpoint, and a limit from the left to work on the right endpoint. Let's do an example. We've got the function f of x equals the square root of 1 minus x. Now, if you know your transformations from college algebra, this is pretty easy to do. We start with the square root of x. We could even think of it like square root of negative x plus 1. The plus 1 shifts it to the left one, but then the negative x reflects it. So we would have some sort of graph like this after the left one motion, and then when it reflects it, we get a graph that looks like this. There's the graph of the square root of 1 minus x. You'll notice it's continuous out towards negative infinity. All these limits would work. And by the way, one notion of the continuity that I might not have said is that it's very similar to the idea of drawing it without picking up your pencil. So it's continuous forever on the left. And then on the right, it stops abruptly at 1. So we can say this much. It's continuous on negative infinity to 1. But the question is, can I put a bracket there, or do I need to put parentheses? Let's look at the limit. The function value is 0. Feel free to plug it in. 1 minus 1 is 0, and the square root of 0 is 0. And the limit, the trend in the graph from the left, is also 0. So with that said, I can use a bracket, because the limit does equal the function value here at x equals 1. Next example. The interval on which the square root of 4 minus x squared is continuous. Well, by a similar method as what we did a moment ago, it's pretty easy to see that this is another circle of radius 2. It's just the top half of the circle. And now you can quickly and easily look and say, hey, the right-hand limit works here, the left-hand limit works here, and everything in between works. So it's as simple as that. Continuous on negative 2 to 2. Brackets because these limits work out as we desired. So for a lot of these, being able to draw a graph helps. Otherwise, just be able to plot a few points and see if you can get a picture of it that way. But this form in general, it's a squared minus x squared. Every time you see that form, that actually is a circle of radius a, just whatever this number is in its square root. It's a good thing to keep in mind. It turns out, based on your limit laws, that continuity holds for a lot of different things as long as continuity holds for the originals. If we've got two functions that are continuous at a point, then at that same point, a constant multiple of the function is still continuous. The sum or difference of the functions is still continuous. The product of the functions is still continuous. And even the quotient of the function is still continuous as long as the denominator is not 0. And you could make up more properties than this, but in general, continuity is very well preserved as long as the original functions are continuous. You can even say a composition. Now this one's a little bit harder. A composition requires you to start on the inside and work your way out. So if the g function is continuous at c, and the f function is continuous at the inside, the g of c, then the whole composite function is continuous at the original c. Here's what we get. We get a lot of functions where we can say they're continuous immediately. And this is what I was hinting at the beginning. All polynomials are continuous. All rational functions are continuous, the fractions of polynomials, when the denominator is not 0. And that's part of the domain. But in general, continuous when the denominator is not 0. Radical functions are continuous when inside is greater than or equal to 0. Because again, that would break a limit law if you got a negative sign inside of a square root. And all the trig functions are continuous. And the only times they would not be continuous are, say, you've got some sort of denominator of 0 also. So we'll do a couple of examples of this. A lot of functions are continuous. And I do say continuous on their domain. What I've really written here, these little notes on the side, is just the types of things that break the domain in the first place. But on their domains, the functions are continuous. Let's do a couple of examples. Cotangent of x, you might recall from pre-calculus, is cosine x over sine x. This function is continuous everywhere except where the denominator is 0. continuous when sine x does not equal 0. If sine x is equal to 0, then x has to be a multiple of pi, if you recall. So x does not equal 0, pi, 2 pi, and so on. But also you could say negative pi, negative 2 pi. All of those values are values of x where the function's not continuous. But otherwise the function's continuous because there's no 0 in the denominator. Next function. Now remember this whole piecewise idea, we just look at the right. X does not equal 0, and we have this function. You guys might remember this function. This is the function that had uncontrolled oscillation. But at 0, we define the function to be 0. I think it's clear that the function sine of 1 over x is continuous when x does not equal 0. You just plug in a value and you can get exactly what you want. But at 0, we had some trouble. Let's think about the limit. For the function to be continuous, this limit as x approaches 0 of g of x would need to equal g of 0 if it's continuous. Let's think about it. G of 0, well, that's just 0 because if x equals 0, then the function value is 0. G of 0 is 0. Now when we're taking the limit as x approaches 0, we're looking at values getting closer to 0 but aren't 0. So really we're looking at this. And as we know, this does not exist. It certainly does not equal 0, and that means the function is continuous when x does not equal 0. But to formally answer both of these questions, it does ask for intervals. For this one, it's going to be kind of strange. We're just going to exclude all of the values that are multiples of pi, and I'm going to do it like this. So we've got negative 2 pi to negative pi, and notice I'm using open intervals. Pi to 0, 0 to pi, pi to 2 pi, and so on. The function's continuous on this infinite union of intervals. It's just not continuous at the multiples of pi. This one's a little bit easier. This is just negative infinity to 0, union 0 to infinity. Next example. Now this one is pretty similar to what we just did a minute ago. Let me go ahead and look at the limit as x approaches 0 of x sine of 1 over x. Now if you recall, we actually used the squeeze theorem to calculate this, and we got 0. With that said, the limit as x approaches 0 of h of x, sure enough, is equal to h of 0, the function value. With that said, continuous on the whole real number line, because this time 0 did not break it. Last thing to bring up for this section is an interesting theorem called the intermediate value theorem. It is a theorem and I don't give its proof, but this theorem gives you a little bit of power to figure out solutions of polynomial equations. If you want to solve an equation, you can take a guess as to whether the equation has a solution by finding a value that's positive and a value that's negative. In general, though, here's the theorem. The function must be continuous on the closed interval. You must have different values for f of a and f of b on this interval. And you've got some value k that's between these two y values, f of a and f of b. Let me draw you a little picture. We've got some continuous function. Here's a, here's b. You've got f of a and f of b. Now if we choose some value k between f of a and f of b, then this theorem guarantees that there is some c so that f of c is equal to this k. And continuity is what gives us this. Let's look at the example. We want to show that the function x cubed plus x minus 5 has a real 0 between 1 and 2. So here's how we do this. We're going to think of k as 0. If I can find an a and a b so that the function is positive above and negative below, or vice versa, then because k is between a negative and a positive, 0 lies between any negative and positive number, then there does exist a 0 there. F of 1 is 1 cubed plus 1 minus 5, which is negative 3. And f of 2 is equal to 2 cubed plus 2 minus 5, which is 5. So, since 0 is between negative 3 and 5, there is a c in 1 to 2 such that f of c equals 0. So what I did was I took this picture, x cubed plus x minus 5, and I have proven that there is a place where it crosses the axis strictly between x equals 1 and x equals 2. Now that we've done this, the question's also saying determine two closer numbers up to one decimal place that bound this real 0. Rather than spend a lot of time trying and doing a few, I'll give you what the two values are, but feel free to pause this video real quick and try plugging in values between 1.0 and 2.0 and try to find the two numbers where one is negative and one is positive, because somewhere between 1 and 2 it will switch from negative to positive. I found f of 1.5 and f of 1.6 to switch from negative to positive, and these are the values that I got when I plugged them in the function. So here's what we have. There is a c between 1.5 and 1.6 such that f of c is equal to 0. Now this is pretty helpful. If you were to continue this process, you could zone in and numerically estimate the solution to the equation, which sometimes comes in handy. Even calculators do this sometimes.